Hey everybody, glad to have you along for the ride as we look at the first fundamental theorem of calculus, the essence of which is evaluating a definite integral using an antiderivative, and I hope to be able to get you started on that. Alright, let's dive in. So the most obvious question is, well, what is the first fundamental theorem of calculus anyway? Must be pretty important because it's fundamental. Well, okay, so if the function f is integrable on AB, ooh, that's a fun word. Integrable might remind you of, say, differentiable. Differentiable meant that we could evaluate a derivative. Integrable would mean that we can evaluate an integral. Yeah. And we are defining capital F function as an antiderivative of the little f function. Okay, so that's a form of notation that's often but not always used, where a capital letter means that that function is an antiderivative of some other function. Another way of saying that is if I were to retake the derivative of capital F, I should get little f. Okay, then we have this integral from a to b of the function little f of x dx. Okay. That we know represents an area. I'll get to that in a second. But this first fundamental theorem is telling me that to evaluate that integral, I need to determine what its antiderivative is and plug in the values of a and b and subtract them. You'll see in an example what that looks like, but for the moment, again, that is an area on the left side, and on the right side, that's a change in the quantity of capital F. Okay, it's the final value, capital F of B, minus the initial value, capital F of A. Another way to think of this is that a derivative, as we learned, represents the rate of change of some quantity, and an integral just represents the change. There's the saying, if you integrate, you lose the rate. We take off the rate part, and we're just left with the change. How much did it change? The area, we must remember also, is a signed area, so the integral assigns a value positive or negative to an area depending on where that area is, above or below the x-axis, and in what direction we're moving from A to B. And we say this area is bounded by, it's enclosed by line x equals a, x equals b, blah, blah, blah. We just colloquially refer to it as under the curve. Okay, so let's look at an example to make this more clear. For the two example problems shown in this video, it's asking us to evaluate each definite integral. Okay, that term definite integral refers to the fact that the integral has bounds. It has an upper and lower bound, which indicates that my final answer is going to be a number. Okay, and the function that we're working with inside the integral, our little f, is 2x to the fourth minus 6x squared. Then we have a dx here, and that signals where the integral ends. It's kind of like a closing parentheses. The integral symbol is the opening parentheses, and the dx is the closing parentheses. That's where we stop. Okay. Then, in order to evaluate this integral, okay, I need to find the antiderivative, the capital F, and then plug in our two bounds, b and a. But that requires, obviously, I need to know what the antiderivative of that is. So, in other words, we need to know a function whose derivative would be 2x to the fourth minus 6x squared. Can you think of what that might be? See, I bet you can figure it out without me telling you how. Pause the video for just a bit and see if you can come up with what that function is. Okay, before I answer the question of what that is, and we'll see if you're right, let me show you a general rule that works for these kind of functions. So what I have here is the power rule adapted for integrals. You may remember the power rule as something we used for differentiation, and the original power rule had two steps. Okay, this is for how to do the derivative of anytime we have x to the something. All right. The first step was to multiply by whatever the exponent was, and then to decrease that exponent by 1. Okay? That would turn something like x to the 7th into 7x to the 6th. But now, if I'm doing the power rule for integrals, I want to do an antiderivative, so I need something like an anti-power rule. Like maybe it's arch nemesis or something. Ha 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 ha. Oh, never mind. I'm sorry. Okay, so that would turn something like 7x to the 6th back into x to the 7th. Okay, I need to basically undo the steps of the original power rule. So the first step would be to increase the power by 1. That's where you see x to the n plus 1 here in the equation. And then I need to divide to undo the multiplication. And I'll need to, because what was originally multiplied is the original power, I need to divide by the new power after I've already increased it by 1. Okay, there is a plus c there. Don't worry about what that is. Chances are where we're at, we haven't gotten to talking about indefinite integrals, so we'll talk about that later. We also have an exclusion that n cannot be equal to -1, simply for the reason that I would be dividing by 0, and I can't do that. Okay. But what if the power is -1? If I have x to the -1? Well, that's just 1 over x. And what function has a derivative that is 1 over x? Maybe you're thinking natural log. That's that oddball that seems to have nothing to do with it, but it's true. And specifically here for future reference, though we won't need it in this video, when you do an antiderivative to arrive at a natural log, you must put absolute value bars around the variable, because we could be talking about either side of the 1 over x function, either left of the x-axis or to the right. Again, more on that in class. Okay, so back to our example problem. Okay, so let's apply this so-called anti-power rule to 2x to the 4th minus 6x squared to see if you got your antiderivative right. I'm going to start with the first term of 2x to the 4th and increase the power on x by 1, so that would be x to the 5th. Then I need to divide the coefficient by the new power, which is 5, so that would become 2/5. For the next term, I need to keep the minus sign and then increase the power by 1, which gives me x to the 3rd. Then divide the 6 by 3, giving me 2. Did you get that? I always encourage you, though, whenever you do one of these antiderivatives, to check to make sure that you did it right. And that's easy. I can check my antiderivative by just doing the derivative to it again, because if I do the derivative to an antiderivative, I would get the original function. Let's see here. Multiply the coefficient by 5, that would give me 2. Decrease power by 1, that's x to the 4th. Multiply the 2 by 3, that gives me -6 because of the minus sign there. And decrease power by 1 is x squared. Alright, so we did it right. But we're not done yet. We found the antiderivative, but we need to now evaluate that antiderivative from -1 to 1. That's what the symbol there means. I drew big brackets around it and put a -1 below and a 1 above. That just simply means evaluate from -1 to 1. Okay, and anytime you evaluate one of these, I strongly encourage you to draw this template. Big parentheses minus big parentheses, for the simple reason that it will keep you from making mistakes with your negative signs. Okay, so that first parentheses represents the antiderivative evaluated at b, in this case capital F of 1, and the second parentheses is for the antiderivative at a, or capital F of -1. I'm just simply plugging in these numbers. So in the first parentheses, I'm just going to replace x with 1, and in the second one, I'm going to replace x with -1. At this point, this would be a safe stop if you're on a free response question, but most of the time these are multiple choice, and so you're going to need to know how to simplify this, and that sounds like fun. First is just, fortunately they gave us numbers like 1 and -1, which are easy to work with. Okay, so that first term would be 2/5, and then the next one would be minus 2, then minus big parentheses, negative 2/5, because negative 1 to the 5th is negative 1, and minus negative 2. Okay, double check that you got the same thing. All right, now time for fun with fractions. Yay! Are you all excited? Okay, so let's see. 2/5 minus 2. Well, 2 is 10/5, so 2 minus 10/5 would be negative 8/5. For the second set of parentheses, a negative 2/5 minus minus 2, that would be plus 2. So 2 again being 10/5, negative 2/5 plus 10/5 would be positive 8/5. Okay, and we're subtracting those, so we would get negative 16/5. How's that for fractions? Okay, so and you'll have plenty of time to practice, don't you worry. All right, so let's look at one more example before we close. Oops, except I wanted to show you a visual representation of what we just did. So here's a graph of the function that we used for little f of x, 2x to the 4th minus 6x squared. And so we evaluated it from negative 1 to positive 1, so that would give us this area. That's saying that area is negative 16/5. Okay, and we can see that the negative part makes sense because this area is under the x-axis. Okay, now for the second example. Well, ain't that a pretty looking function? Those are some of y'all's favorite, aren't they? Well, okay. So, maybe we'll need a little help with that. Like, okay, so we're going to follow the first fundamental theorem of calculus, but what the heck am I supposed to do with that? Okay, well, the first thing you should know to clear something up is like, well, what the heck with that dx on top of the fraction? That seems kind of out of place there. I don't know. And that's shorthand so that when people are printing or writing, it takes up a little less space. But what that really means is the integral from 1 to 9 of 1 over square root of x dx. Okay, so just know that's what that means. There's really a 1 on top of that fraction, and then dx looks like it's in its proper place, ending the integral, and also playing the role, as we've discussed before, of the itty-bitty width of the rectangle as we add up an infinite number of them with the integral. Okay, so, but still, like, okay, what am I supposed to do with that? I'm going to need to find an antiderivative. What have we done with functions like that before to help us when we did derivatives? Oh, we rewrote them. Okay, if I rewrite that in terms of an exponent, then that'll be much easier to work with. So what exponent would that be? Well, okay, we have a square root, and so that would be like an x to the 1/2. And it's in the denominator, so I need to make that a negative 1/2. Okay. And then I still need to do the antiderivative. And this is a power function still. So we'll apply the so-called anti-power rule, increasing the power by 1 and then dividing by the new power. Okay, so I need to increase the power on x by 1. What would that be? Negative 1/2 plus 1 would be positive 1/2, so there we go. Okay, and then I need to divide by the new power, so like that. Oh, that looks ugly. Okay, but it might be, if it's easier if you remember that dividing by a fraction is the same as multiplying by its reciprocal. There. Let's check to make sure we did it right. So we're going to do the derivative of our antiderivative and see if we get the original function. I take 1/2, I multiply it by 2, and I get 1. And then I decrease the power by 1, and I get x to the negative 1/2. Okay? And so another way to look at this too is that it gives me, it's what has to be out in front in order for that 1/2 to cancel and I'd be left with the 1 I had before. Okay? So now we need to evaluate it. We're going to evaluate from 1 to 9 as the integral said. To evaluate it, it's probably going to be easier if we put it back in terms of a root. So I'm going to rewrite it back as square root of x. Set up your template, big parentheses minus big parentheses. If you think that you can do it from here, just pause the video, do it, and then scroll ahead in the video to where I showed the answer and see if you got it right. Otherwise, you can keep listening and I'll explain how to do it. Okay, so in the first parentheses, I'm plugging in the upper bound of the integral, which would be the 9. That's the final value of x. Then in the second one, I'm plugging in the lower bound, the initial value. Square root of 9 is 3, so 2 times 3 is 6. Square root of 1 is 1. 2 times 1 is 2. And 6 minus 2 is 4. Woo! Here's what this function looks like on a graph. And the area that the integral found would be this one, the area from 1 to 9. And that we determined by our anti-power rule that this area would be 4. Okay? For additional verification, we can also look at the squares. Each one of those squares is going to be 0.25 in area. And if you kind of add them up and count them, then that's going to add up to an area of 4. It is worth pointing out before I close that this first fundamental theorem of calculus that we've been working with doesn't just apply to power functions, even though those were the 2 examples in this video. Okay? I can still apply this same rule of finding the antiderivative evaluated at b minus the antiderivative evaluated at a for any other kind of function as well. I just have to be able to determine its antiderivative. So just as a very fast example, I could do an integral of the cosine function. The antiderivative of cosine would be the sine function, and if I took the derivative of sine, I would get the original cosine back, so that's how I know that sine is the antiderivative. And then, again, plug in the upper and lower bounds and subtract. So keep that in mind that it also works for any other kind of function if I can determine what the antiderivative is. Alright, that's it. I will see y'all in class.